The following is a review on stoichiometry. I'll be going over 3 potential problems that you could be working on when encountering stoichiometric equations. I urge you to pause the video when indicated and work out the problems yourself before I reveal how to work through the t-charts. Let's begin. Our first problem. How many grams of aluminum oxide would be produced if 2.7 times 10 to the 23rd atoms of aluminum reacts in excess oxygen? Okay, before we start to do any calculations, there are 2 things that I urge you to do. The first is to always check the chemical equation and to see if it is balanced. So in this case, the aluminum and oxygen are not balanced. So I see my oxygens need to be a total of 6. And that results in having 4 aluminums. Secondly, I want to organize my information. Okay, so I have my flow chart in the upper right from grams, moles to particles, and then I can go to the other side through the mole ratio. Well, that doesn't help me if I'm unable to understand where I'm starting and where I'm ending. So I'm going to try to organize my information by reading it out of the description, out of the problem. So it says how many grams of aluminum oxide. So I want aluminum oxide. So this is grams of aluminum oxide. That is what I'm solving for. It would be produced if I have 2.7 times 10 to the 23rd atoms, which I'm just going to call particles. So looking at the flow chart, maybe you can already figure this out of how many steps you're going to need. But for this first problem, I'm going to help highlight this. I'm starting in particles. I want to end in grams. So what does that mean? Well, I urge you to pause the video and work out your t-chart. If you're having struggles, obviously you can always start it up and see how I'm working on the problem. So we always start with what we know. And what I know is I have 2.7 times 10 to the 23rd particles of aluminum. I have my number, I have my unit, and I have my label. If I'm in particles and I need to get the grams of the other substance, that is going to be a 1, 2, 3-step problem. So it is really important to set up your t-chart to reflect that. I am solving for grams of aluminum oxide. If I write that there, then I'm able to see what my destination is. So, letting my units be my guide, I have particles of aluminum, so I bring particles of aluminum down to the bottom. So that is this step right here in the upper right. So whenever I'm using particles or atoms or molecules, I'm always using Avogadro's number. So that's 6.022 times 10 to the 23rd particles of aluminum. I'm going to moles. So that is moles of aluminum. And we always say that's 1 mole. 1 mole equals that number. Okay, now I bring that unit down again. Now I'm heading into the mole ratio step. The mole ratio is the ratio of my 2 different species. So I'm starting with aluminum. I'm ending with aluminum oxide. So I'm going to the other moles, the moles of the other compounds. So you could think of it this way. If I erase everything on my flow chart, this side is all my aluminum. This side is all my aluminum oxide. Every label, grams of aluminum, moles of aluminum, particles of aluminum, this would be moles of aluminum oxide or grams of aluminum oxide. So if I'm going to the moles of the other compound, it would be moles of my aluminum oxide. And what are my numbers? They're in my balanced equation. I have a 2 there. I have a 4 there. Those are my mole ratios. Units, I bring the unit down. It's always 1. And then where am I going now? I'm going up to grams. And every time I use grams, I have to use the periodic table right? So what am I using? I'm using 2 aluminums. I'm using 3 oxygens. I look up on the periodic table. Aluminum weighs 27. Oxygen weighs 16, which makes a total of 102 grams. So now we just calculate this out. And I get an answer of 22.9 grams of aluminum oxide. So that is how we do a simple T-chart using 3 steps, solving from particles to grams. Let's take a look at our next problem. It says, how many grams of water are produced if 25 grams of pentane reacts with 50 grams of oxygen? So again, let's balance our equation. I need 5 carbons. I need 12 total hydrogens. 5 times 2 plus 6, 16. So I would need 8 oxygens. So let's organize our information on this one. It says how many grams of water. So I want grams of water. It says if 25 grams of pentane reacts with 50 grams of oxygen. So I'm going from grams to grams. So what I'd suggest and urge you to do is pause the video and try to solve this problem. So hopefully you recognize what this problem is doing is that you have 2 masses on the left side. These are both reactants. So when you have 2 of them, you have to determine which one's going to run out, which one's going to make the least amount of water. So I am starting with grams of one compound, and I'm asking for grams of another. So this is a 1, 2, 3-step problem. So what I need to do is I need to solve this twice. There are some other ways to do this, but this is definitely one option. So grams to grams is 3 steps. So I'm going to set up the framework. It's grams of water, and then I'm going to do it again with my oxygen. Be very organized. Let the units be your guide. So right away, this is grams of C5H12. Where do grams come from? Grams come from the periodic table. 5 times 12, which is carbon, plus 12 times 1 is 72 grams. That's the molar mass of pentane. Well, that equals 1 mole of my pentane, because that's one of them. Again, look at the flow chart. I'm going to moles. Now I'm in moles. I'm going to the other moles. So I need to get rid of this compound, and I'm going to the other compound. And the other compound I have established is water, because that's my question. So what goes there? Well, when I have 2 moles on the same line, that is the mole ratio. So I need to look on my balanced equation. So in this case, I have 1 C5H12 for every 6 moles of water. Now I bring moles down. Many of you want to put a 6 there, but what I'm saying is that 1 mole of water weighs a certain amount, and then I have 6 of them on that middle line already. So again, grams come from the periodic table. I'm going up to grams here. So 16 plus 2 is 18 grams, and now I'm going to calculate that out. And I get 37.5 grams of water produced if I have 25 grams of pentane. But what if I had 50 grams of oxygen? Same concept. Bring the oxygen down. O2 is 16 times 2, and that's what 1 mole equals. Bring the moles down of oxygen. And now I'm going again to the other compound. So I'm doing the mole ratio right now. So like we have it, that I have the exact same ending because I'm solving for water again. Okay, I'm going to the same compound. So what is my missing number here in the mole ratio? Well, oxygen has an 8 because that is the mole ratio from the balanced equation. So this is going to give me the amount of water made from that amount of oxygen. I multiply the top, I divide the bottom, and I round just slightly, and I get 21.1 grams of water. So what is my final answer, and how do I interpret this? What it means is if I just had that much C5H12, I would make 37.5 grams of water. If I had 50 grams of oxygen, I'd make 21.1 grams of oxygen. So I'm only going to be able to make the least amount. So I box the answer. Little bonus question. What is my limiting and what is my excess reactant? Well, a lot of people will label the boxed area as the limiting reactant, but you have to make sure that you are being specific. The reactants are my C5H12 and my O2. My O2 is going to run out, and my C5H12 is going to be in excess, based on the fact that the oxygen makes the least amount of water. Final question. It is found that hydrogen's production was only at a percent yield of 65.7%. If 2.5 moles of sodium reacted in excess water, what was the actual yield in grams of the hydrogen production? Okay, very confusing, a lot of words. This is why we organize our information. First, let's balance our equation. I wrote water on purpose like this because water breaks up as H and OH. So this makes it easier. I have one H on the left, I have two H's on the right. So if I make two H's, now I have two OH's, two OH's, I have two NA's, I need two NA's. So let's organize the information that I was given, even if I don't quite understand what it's saying. It's saying that I have 2.5 moles of sodium, and it's saying that hydrogen's production was at 65.7%. And that's all that says. And then it's asking, what is the actual yield of hydrogen? Okay, actual yield and percent yield is a percentage. You take two numbers and you divide them over each other. So I'm going to place this over here. So what do we know? Well, this is what we know. Is that actual yield over theoretical yield equals a percent yield, how much you made. So it appears that we are looking for the top number, the actual yield. I'm going to call that X. And they gave me a value of 65.7% of my percent yield. So I'm going to turn that into a decimal. So the only thing I don't know is theoretical yield. Well, that I need to use a T-chart. So I probably have done more than I should at this point, but pause the video if you haven't already and try to work through the rest of this problem. All right, you always start with what you know. So I have 2.5 moles of Na, and I want grams of hydrogen. So let's think about this. If this is Na, and I want hydrogen, that's what this would be, right? Two different compounds here. What am I starting with? I'm starting with moles of Na. This is where I am already. And I want grams of hydrogen. So how many steps is that? Well, it looks like it's two only. It's only 2 steps. You have to make sure you're reading the flowchart correctly. So I bring moles of Na down. And immediately, if you look at your flowchart here, I am already on the mole ratio. So I need to use the values from the balance equation. So there's a 2 in front of the Na, and then I'm going to the other moles, and that's hydrogen. And there's simply a 1 there. I bring the moles down of hydrogen. I always say there's 1, and I'm searching for grams of hydrogen, because that's what the question's saying. So 1 times 2 is 2. And now I need to calculate that. And based on the numbers, obviously, it actually ends up being 2.5 grams of hydrogen because those two different number 2's actually cancel each other out, which is fine. So what am I going to do with that now? Well, this is what should have been made. And what should have been made is my theoretical yield. So that's 2.5 grams. So if I have 65.7% of a percent yield, how much did I actually make, my actual yield? Well, you're going to take 2.5 times 0.657. to get your actual yield. And that results in a value of 1.64 grams of hydrogen, which would go right here. This is 1.64 grams instead of my x. If you're not sure, you can always check it, and 1.64 divided by 2.5 would be 0.657. So that is a percent yield problem. The other way that it could be asked is it could be already be given an actual yield, and then you'd find the theoretical yield, and you divide those, and the question would be asking what is the percent yield. So I hope this helps. Please note the numbers, the units, and the labels. Those are all extremely important. Have attention to detail so you can keep track of your numbers and your calculations.